Yes, you are.
Hello.
Yes, you are audible.
Thank you. Good afternoon, good morning, and good evening in whichever time zones you all are. Let us begin the parallel session of this AIT Tech Talk. And I would like to start with by stating a comment that the structural assessment of existing buildings would govern the future of structural engineering. So this is because while approximately the construction of new space is just 2% annually in countries like USA, it is deemed to further reduce over the next few years and decades in most of the countries, mainly due to the construction surge saturation and the construction of all the buildings that are happening right now. The domain of existing buildings would be more prominent, and these buildings need to be maintained and managed for the reduction of its capacity due to various reasons and increase in its demand due to natural or man-made hazards. Today, I, Chaitanya Krishna, a faculty of Asian Institute of Technology in Structural Engineering, specialized into seismic assessment of reinforced concrete building, would be introducing the concepts of structural assessment of existing buildings, the challenges, opportunities, and our experience in conducting academic research and real projects, along with Dr. Prameen and Ziauddin. So this will be followed by an interactive session. And if you are a student, faculty, or a professional, or a structural engineering enthusiast, this is a forum for you to ask questions, make your comments, or state your observations. So I would request you all to type in your questions in the chat window, and the questions will be taken up following the presentation. And after the presentation, you can also raise your hand and ask questions or create a discussion point. So let me start with saying that the fundamental reason for assessment of existing buildings would be attributed to either reduction of capacity of the building or increase in demand on the building. The capacity reduction could be due to aging of buildings, past hazards, non-engineered or bad construction, or weather or climatic degradation that we have started observing recently, or deviation from designated use of that particular building type. And the increase in hazard could be mainly due to the change in the level of hazard that was considered at the point of design of building, or maybe some particular hazard which was not considered at all due to various bureaucratic and technical reasons. So the application of these capacity assessment would range in a various kind of areas, such as operational evaluation, which includes the post-earthquake or post-disaster investigation to know the occupancy level of the building, or risk assessment by the governments for creating disaster management plans, retrofitting or maintenance and related studies, or improvement of existing guidelines or codal provisions for future buildings, or creating awareness among communities, or using this as a outcome for innovation in construction industry or retrofitting industry. So where do we stand? We stand in between the real world and the analysis world, where real world is full of unpredictable threats, large building stocks, unacceptable construction practices, and huge scatter in the material uniformity, creating a huge amount of uncertainties. Whereas the analysis world, which is mostly comprised of the mathematical components such as geometric material modeling, or the structural capacities, or considering failure behavior. So we structural engineers try to bridge the gap between the real world and the analysis world with the principles of 4 A's, that is ability, accuracy, applicability, and acceptability. So the engineering categorization of these analysis methods could range from the late 1800s, where the expert opinion based approaches were used in the beginning to conduct the analysis of existing methods when the computers were yet to arrive, and all the methods were yet to be in place where they are today. And as mentioned by the previous speakers in the morning sessions, I think it is very important to know that structural engineering is 80% of common sense. And as the age progressed, we went for rapid visual screening or post disaster assessments through questionnaires, or through visual inspections, or by using some basic measurement equipment to understand the behavior of buildings after a disaster, and using that as a knowledge base for future constructions, etc. The analytical assessment approach is mostly the numerical stuff that we do on softwares, on the nonlinear analysis softwares that we have been using as structural engineers. And a more recent approach, or the more popular approach in the recent times, includes the use of non-destructive testing and structural health monitoring. So broadly, these are different approaches, and a combination of two or more approaches is the most desirable one. And the analytical approaches and the experimental approaches are the hot ones that we are currently trying to develop and do a lot more projects and research in this particular domain. And coming to some of the recent methods that we are interested in are structural health monitoring, where experimentation and system identification had started a few decades back. And now it is coming into practice in terms of analysis, so that the level 3 and level 4 of identifying the existence of damage and quantifying the severity and location of the damage has become a fast moving research area in terms of structural health monitoring, with the increase in availability of different kind of testing methodologies that we have right now. And one more area that is gaining attention in the recent times, and is one more area where we are also interested in working with, is machine learning, which is more meticulous and superior, especially when the data set is fuzzy, vague, or noise contaminated. And the application of this artificial intelligence is in various areas, such as damage inspection using digital image correlation, or using this for structural system identification, or seismic performance assessment, or material modeling, or estimation of capacity of the structure. What we are more interested is using machine learning for vibration control and structural health monitoring in future, so that the material property identification becomes a lot more data centric and lot more reliable, so that whatever values you put in your numerical tools have a lot higher meaning with respect to the available data that has been collected in the last few decades. Some of the academic research topics that we have been working on would be shown here. So this is one of the topics where we try to merge a force vibration test called as experimental modal analysis, and a free vibration test, which is operational modal analysis. We combine them with the help of numerical techniques, so that we could get modal parameters, and the modal parameters can be transformed into a physical parameter to be used into numerical modeling, such as finite element methods, etc. Another research topic is this is a problem-based topic where buildings in Nepal particularly have businesses on their first floor, and because of these businesses, the buildings have the problem of soft story in the aftermath of an earthquake. But then merely asking people to just close their business by using a retrofit cannot be a direct solution. Having said that, there are two major problems. One is the economic affordability of people living in these houses, and the second one is asking these people to close their livelihood, which comes from the businesses or parking lots, etc. So Academically, what we tried to do is use the mathematical concepts or concept of numerical optimization to optimize between the strength or safety required for the landlord by making sure that there is enough or adequate space for him to run a business inside this. And at the same time, not using steel or not using BRB braces is another way of reducing the cost involved in this particular retrofit. So as an in an academic approach, using a technique called sequential quadratic program, we could optimize the usable space with respect to the strength, and found that the strength of these buildings were increased um, by allowing some amount of business space for these people, and by making use of concrete as a retrofitting material, the cost or locally available retrofitting material was achieved in this research. In another research, we were trying to find the problem of non-engineering defect in countries like India, Nepal, Pakistan, Bangladesh, or many other Southeast Asian countries, where there are plenty of problems. Like one of the problems that we identified was improper rebar splicing. But this is not just one problem. There are plenty of other problems with respect to the construction industry, which is highly localized by the inexperienced and non-technical masons. So studying this experimentally would take ages to cover up all the problems that we have in our sites. So therefore, a low-cost experimentation by using microconcrete and a combination of numerical modeling had been used in this approach, so that the cost of experimentation is lower, and the alternative arrangements or alternative possibilities could be evaluated numerically by validating the experimental model to study variety, and a large number of case studies could be done by using this kind of an academic research. This is another research in which the blast analysis was summarized. So here we have highly nonlinear modeling softwares in practice. Now, one of such softwares is called Extreme Loading and Structures, which follows applied element method technology to model blast loads. However, unlike blast loads, unlike wind loads or earthquake loads, blast loads do not have a comprehensive assessment procedures. For example, such questions like how to compare different blast loads on a building. Why is the capacity of frame subjected to blast load? What is the capacity of frame subjected to blast load? How to strengthen the building to withstand blast loads? Or what is the effect of debris fall? Or is the debris lethal? Etc. are the questions that cannot be answered from numerical modeling alone. So what is needed is a comprehensive blast response analysis. So in this research, what we do is, from the highly nonlinear modeling that we get, the results we get is summarized into structural blast, debris analysis, and residual capacity of the frame. So with this, you can summarize blast for different kinds of cases of buildings, or different kinds of claddings, or maybe you can strengthen the building and then apply blast. So different cases can be compared, like in the case of earthquake or wind loads on structures. Coming to the real projects that are being executed in AIT, I would like to show you about a project in Philippines for which the methodology followed was to measure the dynamic characteristics of a building before an earthquake and after an earthquake, and the modal identification has been done for both of these cases, and a preliminary evaluation has been done to proceed to a detailed investigation. For this purpose, a baseline measurement and post-earthquake measurement was done, and The result, after analyzing the model properties, we could see that from the preliminary evaluation, the change of natural period had shown some damage, and therefore it was recommended to go for a detailed investigation in this project. In another retrofitting of a 5-story school building in Nepal, we followed the procedure of three stages. In the first stage, collection of building information was done, including the material and geometric properties, and a performance-based evaluation of existing building and strengthened building with our recommended retrofitting procedures was done. For this, a school building was considered, which suffered damage in Gorkha earthquake, which was modeled in SAP, and 3 different retrofitting methods, that is column jacketing, shear wall, and buckling restraint braces were recommended and modeled in SAP to evaluate this. Nonlinear static pushover analysis was conducted to find that shear walls were more effective and column jacketing was highly ductile at the global level, but further member level investigation was needed according to this project conclusion. And some more similar projects executed in AIT includes a 4-story hotel building in Nepal, for which shear walls were proposed based on performance assessment. And a retrofitting or re-strengthening strategy was investigated for a reinforced concrete building in Bangkok with the same column jacketing, shear walls, and steel bracings. And a similar reinforced concrete frame building in Nepal after Gorkha earthquake was evaluated for a proposal of shear walls in the building using ETABS and perform 3D. A similar investigation in Bhutan to verify the adequate demand capacity ratio to see whether the building was safe or not was executed. To summarize, I would like to say that while we have buildings getting damaged due to catastrophic earthquakes, we also have buildings like what is shown in this figure, where the building had collapsed without an earthquake, without a wind load, just due to over usage of building and poor construction practice and inappropriate use of the building, deviating from the designated use, had caused such damage. So these kind of situations put us in various kinds of challenges and needs. And the various kinds of challenges include the large building stock and growing constructions with non-uniform material properties, and not knowing the reliability of non-destructive testing, and the incapability of modeling highly nonlinear behavior are the major challenges. And some of the major needs include the need for convenient and reliable testing. Improvement of codal provisions and guidelines is an important need. And we also need a lot of cost-effective experiments, because a large number of experimental knowledge is needed to overcome the problems we have in structural engineering. And we also need reliable modeling tools and reliable modelers, like what was mentioned in the morning session, that many structural engineers should choose to become programmers to develop their own softwares. And we also need modern tools and techniques, including software as well as hardware. And this turns into various kinds of opportunities. In academic, we need to use interdisciplinary approaches for testing and analysis of methodologies, and we need hybrid model updating to identify material properties from the ambient tests. We need to use the cutting edge machine learning, supervised or unsupervised machine learning, to estimate material properties and reduce the human effort involved in assessment of existing buildings. And we also have to develop high-speed analysis tools to cater for the need of highly nonlinear behavior, like I had shown earlier. And some of the real projects include retrofitting methods, development of maintenance guidelines and procedures, operational evaluation of building in the aftermath of an earthquake, development of risk and vulnerability maps of societies, and development of disaster management plans. If you are interested in collaborating with us in some of these analysis of existing methods, this would be the contact information for you to do so. Thank you very much. I would like to open the floor for question and answers. Zia, can you help me?
Yes, you can see me, right?
I hope so. Yes.
Okay, all right. Actually, we already have like 3 questions. Let me start with that, and then yeah, after that we'll have more question and answer session. It will be in fact a bit more of a discussion session. The first question that I received is from Ayman. His question is, what is the software used for blast loading numerical simulation?
Okay, just a minute. Let me go to the slide. Okay, the software used for blast loading simulation is called ELS, Extreme Loading and Structures. Is Ayman there?
Hi, Ayman. So,
hello, Ayman.
Hello. Okay, so I can move to our second question, but Ayman, you can always come back and ask the.
Yeah, Ayman is there.
Yeah, he replied that yes, I'm there. So hi, Ayman, the answer is okay, or you have more questions?
Name of the software is Extreme Loading and Structures by Applied Scientist International. It's a paid software, but it depends on applied element method. Applied element method is different from finite element method, where finite element method works on the principle of node connectivity. Applied element method works on the discrete element principle, where the connectivity between elements is governed by a connecting spring, and the disconnection of spring is allowed in this particular methodology, and therefore highly nonlinear behavior such as blast or earthquake collapse can be modeled using applied element method. If you are interested in knowing about this, we are working on applied element method in AIT. So you can come contact us through AIT solution to know about this.
So we already answered the second question, which came from Mr. Ashish Sapkota. Hey Ashish, how are you? He was a student of Dr. Navid, and I also worked with his thesis. So his question was, what are the benefits of using AEM over FEM, and which one will produce a better result?
Okay, so AEM and FEM are two different tools. FEM can produce really good result in small deformations, such as elastic and beginning of nonlinear behavior, whereas AEM follows the principle of material nonlinearity and geometric nonlinearity, and has certain issues with in implementing Poisson effect. Therefore, AEM is a lot more accurate in the case of larger deformations, and FEM is a lot convenient in smaller deformations. And once the crack opens in FEM stops working, because in FEM, the material properties and all the constitutive relations have to be shared at the node. And if the material separates, the gap has to be filled with a dummy material. And at that particular point, the computational effort becomes very, very expensive. It's numerically very expensive to model large deformations in FEM. And a lot of research is actually going on in this area. So in case, to answer in short, AEM is a lot more accurate in large deformation. FEM is accurate in small deformations. Next question. Yes.
Okay, so Ashish, you are happy with the answer, right?
Yes, sir. But there are a few more questions. Maybe we can.
Yeah, it's okay. You can ask directly as well. Yeah.
Yes,
just
sir. I'm a little bit Yeah, you talked about some kind of connectivity, right? So can you please tell me a little bit more about the connectivity, about the springs, or there are some other kind of material that we need for the connection?
In case of FEM or AEM?
AEM.
In case of AEM, we don't have a dummy material in between two elements. We follow rigid elements. We have two rigid elements. They are usually connected with springs. And the spring, each spring comprises of two different springs. One is a normal spring, the other one is a shear spring. So the normal springs takes the material nonlinearity of compression and tension, and the shear spring takes the material nonlinearity of shear material model. So compression, tension, and shear are handled at the spring level, and the deformation are handled at the element level. So you have one element here, you have one element here. Both these elements are connected by two springs, a normal spring and a shear spring. The material properties are handled at this location at the spring, and the deformations are handled at the element level, and therefore geometric modeling is done at the element level. So once the crack opens, simply the spring gets cut, but the geometric modeling is still there in place. So the material deformation can still happen in this case. So this is the premise of AEM, but if you are further interested, you can contact me.
Okay. So one more question.
Yes.
So if you are talking about the timing, like timing to run the analysis, so will it take a little bit more time or less time as compared to FEM modeling?
It depends on what kind of modeling you are doing. So for example, AEM is purely solid element modeling. So you have solid rigid blocks connected by springs. In case of FEM, you have multiple choices, right? In case of ETAPS or SAP, you can do beam element, you can do one column element. So one whole column is considered as one element, right? So in case of AEM, you can have multiple elements for one beam or one column. So in that case, you have multiple elements. So if you compare apple with apple, and oranges with oranges, in case of AEM, if you use multiple elements, you want to see the failure at each element, and you compare it with FEM of that sort. You take solid element modeling in FEM through Abacus or some softwares which can actually handle solid elements. The time of computation should remain the same.
Thank you, sir.
But then if you use SAP or ETAPS by beam models or column models, then the number of elements will be very less. Number of elements will be equal to the number of beams plus number of columns in a very vague sense. Of course, there will be a lot more complications to it. So the number of elements will be a lot less in comparison to AEM. Then the simulation will be much more faster in case of FEM. But is it accurate in the nonlinear phase is a question that you need to answer. As a structural engineer, I think you should judge what resolution of simulation you need to do.
Thank you, sir.
That was a very good question.
There is a follow-up question. I think it's from Joselito. I pronounce it right? Joselito. All right. The question is like, how do you model or input a seismic nonlinear forces in both software? I think you're referring to AEM and FEM, correct?
Can you elaborate the question a little bit?
The question was like, how do you model or input the seismic nonlinear forces in both of the software? The question is, how do you model nonlinear? Do you model nonlinear in AEM and FEM?
Yes, you can model nonlinearity in AEM or FEM by specifying the material properties. Application of SMICE. So this is little difficult to understand. I think you mean to say, how do you input the seismic forces and how do you model nonlinear behavior? Right?
I believe so. Jocelyn,
so
can you
these
elaborate?
are two questions. One is, how do you input seismic forces? And how do you model nonlinear behavior. So to model nonlinear behavior, your software should have the ability of doing it. So first of all, so usually the nonlinear behavior is is handled by use of material modeling. Your elements will take forces irrespective of whether they are seismic forces or wind forces or whatever be the forces that you apply in the standard force deformation equation. So the basic physics of the equation is kx equal to f. K times x equal to f. So if you are applying external force F, the right hand side will take care of the force. In simpler terms, there are different aspects to it, but in simpler terms, the right hand side F will take up all the external forces, whether it is wind force or earthquake force or any other kind of force. The left hand side, which has K times X, K is the stiffness matrix. At each increment, you apply nonlinearity based on the material models. How do we get material models? Material models we mostly get from the experiments we do at the labs. In case of concrete, we compress a concrete in a compression testing machine to get the concrete compression envelope. Similarly, we apply a diagonal compression test on concrete to get its tensile strength. Then we get the shear test. We get the values of these material models, and whichever software you are using, depending on the kind of development that was employed, it might have some kind of envelopes inbuilt in it to handle these material properties. So your tested material properties are given as inputs while doing the material modeling, and the forces are applied externally, and you simulate so that the x is calculated from kx equal to x at each time increment or load increment, and that's how you do seismic nonlinear forces, or you do this, if that is what your question is.
In other words, Doctor, it seems that what you're telling me is it is actually force-based or displacement-based. That's actually relatively different.
Pardon? Sorry.
Yeah.
Voice
So
is.
generally, the difference is one is you're referring to. It becomes now a displacement-based or a force-based.
I think I understood your question most likely.
Okay.
You're saying like your response we are getting that is force based or just displacement based. I mean, your question is like, is it compatible for the local response and global response, correct?
Because if we're referring to a particular hinging system in any skeletal structures or even a general finite element system, either we identify the particular material behavior of one joint or system. So we can even monitor the effect of those hinging or a combination of sorts of all hinging systems on a drift or a particular displacement of one structure just to monitor. In other words, as you said as a while ago, rather than inputting the full nonlinear effect of cyclic loading, it becomes a time step of one single force and identify the rotation or behavior of particular hinging system and monitor it based on limits, performance limits that we use or declare. Is that what you're referring to?
Jose Lito, I'm very sorry I couldn't hear you because of too much of background noise.
Yes, I think the background noise is coming because he's maybe using multiple devices. Most likely, it looks like a signal
Okay.
description. Okay. As far I understood, like his question is like, is that software is capable for the local responses? This is what I have understood at the beginning. Like
Oh.
the hinges, like for example, in finite element model, when we model a structure, we can get each and every joints, forces, and also the deformation. It can be done also. So it looks like that AEM software has taken all the attention. So yes, so I think that is the question, if I understood correctly.
Okay, so I heard that he was asking whether it is displacement based or force based. I would say
Initially, yes.
initially. The answer is in case of AEM, it is displacement based. We calculate stiffnesses of the springs and then transform the stiffnesses at the elements, and we do the computation incrementally, and the computational method is implicit way of computing. In spite of the fact that we could model blast and separation, we do it using implicit, number one. Number two, formation of hinges, etc., is implicit in nature. So we do the material modeling, formation of hinges happens automatically because it is a solid element model. We are not using beam elements or column elements here. For example, if we have a beam is split into multiple cubes connected with each other through springs. So in this case, formation of hinges is automatic. And if you want to understand hinge formation, like in the case of FEM softwares, you may have to develop your own subroutine to do so depending on the purpose of your choice. For example, my students, if they have to study about soft story problem, and if they have to have natural frequencies or mode shapes, they would write their own subroutines to do the modal assessment using shift iteration technique. Or if they have their own, if they do blast loading, they would develop blast subroutines by themselves and use it for their research. So this is at the research level. The commercial software 3D AEM by ELS offers almost all these services that are available in the competitive finite element modeling softwares. So I'm not a big expert of the commercially available software, but I can tell you about what is the backend of this software, how we are developing it. We are developing our own version of applied element method in 2-dimensional and 3-dimensional computations both.
So eventually you answered the question of Mr. Anuj, whose question was how would you incorporate the concept of AEM in the traditional software? Or do you have separate software for the implementation? I think Dr. Krishna already answered that.
At the moment, we do not have an integrated software, but there are initiatives of combining AEM, DEM, and FEM into one single software. If you want AEM commercially, ELS is a company who has a commercial version of AEM, and it is widely used in United States and many other parts of the world. Middle East exclusively uses this software for blast analysis, so that when you blast a building, you would know at what offset your building blast periphery has to be defined, so that the debris doesn't fall onto the next place. And you can also judge on where to blast, where to keep the blasting material in the building. So this is with respect to controlled blasting. This is with respect to controlled blasting. I'm not asking you to blast your own building. So this is with respect to illegal constructions, and some buildings have to be blasted for reconstructing. This is in the field of controlled blasting. Yes. Next question.
So there are a bunch of questions. I think all are for Dr. Pramin.
Okay.
Two of them coming from Niharika. One is like she referred to slide number 16.
Yeah.
And
could you move to slide Dr. 16 also?
question is like, what was the difference in analysis found with two different softwares, Perform 3D and ETABS, and used for the evaluation of four storied RC buildings? Is that one is better and other is unacceptable? That is one. Another is, how are you modeling the hinge behavior for the retrofit sections? A similar question came from Dave Ramos as well. Yeah, two questions from them. Another question is from Matt. How do you model the column jacket or retrofit method in your analytical model? So three questions for regarding the software applications.
Okay, so yeah, you can repeat the question again. Anyway, I will start with the first one first.
Yeah, first one.
Okay, regarding to the slide number 16, how can we select the what is the different software between Perform and ETAP based on this slide? As you see, they have some background story when we use the tool to analyze the work when we carry out the work, because all projects they have the limitation of the time. Actually, we will go to any software that we the most familiar with. Okay, because seismic evaluation based on the SCE 41, we need to evaluate the existing structure based on two levels of earthquake for the small earthquake and large earthquake. For the small earthquake, the response tend to be linear only because it's small earthquake, it's frequent earthquake. For the large earthquake, like up 2,500 year MCE level, it will go non-linear lane because it will large earthquake. We will never design building to receive that kind of force. I mean, in terms of strength. Okay, so ETAP, we familiar with the linear analysis. We easy to model for the linear. We choose that one. Okay, and for Perform, we familiar to perform with the nonlinear analysis. So that's why we choose that one. It doesn't matter. You can use both level of earthquake with ETAP or SLAB or Perform if you're familiar with. So to manage the time on that time, I want to do something quickly. Go for linear with the ETAP, start it easy, and go for nonlinear for Perform. That's the story. And we normally do like this. We start both model in the both platform, ETAP and Perform. We always calibrate both model by see the dynamic property for both to calibrate for each. That is the story. Okay, for the first one, I think it should be clear for this one. You can use any actually if you're familiar with. Okay, because you need to validate something first before you use that kind of tool. The second one, I will move to, okay, how are you modeling hinge behavior of retrofit section concrete jacketing in SLAB 2000? Okay, to model the nonlinearity to the structure, to the frame element, they have two main concepts. You can put the lump plastic hinge and you can put the fiber approach as well. Okay, for column jacketing, I use section designer. Okay, section designer. They have that option. You can draw the existing structure, existing section with the reinforcement. You can put the concrete fiber. You can put the rebar fiber for the existing one. And then you can draw over again to the boundary for the new section that's assumed to be concrete jacketing. Based on this section, the assumption is the connection between new and old is perfectly connected. Okay, we need to design later with the shear key that can receive that kind of force. We will check later. But the concept to model for this one, I use fiber and I use the section designer in SLAB 2000. That is the concept. And if you use plastic hinge for beam, you can simply draw the section designer as well. If you want to use that the section designer, or you can simply calculate for the plastic hing to put the nonlinear hing, plastic hing. That's another concept also. But the one that we need to check the connection between the existing element and the new concrete. We need to decide the shear key for those when we propose the jacketing. Okay, they have the last one, Sia.
Okay, there is a follow-up question because you already answered the question of Matt. His first question was how do you make an analytical model? The follow-up question is what is the reference we use for the nonlinear to get the nonlinear properties for the retrofit model? He asked for the reference.
The reference, like okay. So actually, like this, when we do the seismic evaluation and retrofit based on the analysis approach, not experiment approach, based on the engineering practice, we need to go for some standard. The standard that we normally follow is ASCE 41. Okay. In this standard, it contains all the nonlinear modeling parameters. You can model the backbone curve because they collect many data from the experiment also. They have some sample parameter that you need to calculate something. You can model backbone curve for that one. ASCE 41. If you have the experimental result, you can directly apply that thing as well. The guidelines allow you to do that. That is a reference. You can go back to see the other guideline like a FEMA also. They have many kind, but it depends which guideline that you choose for your project. Okay. For me, I just said first it's a ACE 41. You can follow that one.